Welcome to the third lecture. We're going to start a new topic today. We're going to start talking about knowledge representation a little bit, ontology, schemas, semantics, logic, reasoning, this sort of stuff. So we're going to have about 4 classes on this topic. So the last time we spoke about the semantic web, and we spoke about how we could model data as a web standard. Yeah? So we spoke about RDF, and in the lab you model some data about, I don't remember what series was it, a TV series, using RDF, so given some text. So you see how the triple model corresponds also to a graph. So we managed to visualize this. So in terms of the modeling, 2 key aspects are the properties that we use, which are like the labels on the edges, on the directed edges. So first air, title, start, RDF type, first movie, and so forth. And the second important thing are the classes, which are the things where we group similar entities or individuals into classes. For example, we can say that all the movies are of RDF type movie. Yeah. So today's topic, we're going to cover the start to cover this second layer of logic. Yeah, this second layer of how can we do some automated reasoning and define the semantics of what we're talking about. So on the logic, as we saw in the first class, we have these 2 rules here. B capital A implies that A is part of B, is one thing. And we have a transitive rule here to say that A part of B part of C implies A part of C. Yeah, so these are rules that we can apply for inference. We're going to be looking at rules, but we're also going to be looking at ways of applying reasoning using something called ontologies, which we'll talk about. Okay, so the first question is, how can we capture logic on the semantic web? And this has been a big debate in the research community, and people still argue about this quite a lot. So it would be useful if we could capture the semantics of the terms we're using in the data, particularly the properties and the classes. But the question is, what is the best way to do that? And there's a number of options that we can apply. The way that has been most adopted in the semantic web is, instead of using rules, to use triples with special meaning, effectively. Yeah. So rather than using rules, we can instead try to model the semantics of our RDF graph within the RDF graph itself. Yeah. What does that mean? It means that we're going to use some special kinds of triples that have special meaning when we're building our RDF graph. So we can define relationships between classes and properties and give these relationships well-defined meaning. So what kinds of relationships could we possibly think about modeling just to start with? Yeah. So here we have a bunch in blue, we have a bunch of classes, and here we have a bunch of properties. Yeah. So we see that some of the classes and some of the properties, or one class and one property, have this FOF prefix. This is a well-known vocabulary in the semantic web for people. It's called friend of a friend, for kind of modeling decentralized social networks. Okay, so we have some classes, we have some properties. Let's think about the classes first. Sorry. Forget about that. What kinds of relationships could we identify between these classes? Is there some sort of relationships, general high-level relationships we could identify? So for example, between a capital city and a city, obviously there's some relation there, right? And what is that relation? We could say that if something is a capital city, for example, if Santiago is a capital city, it would imply that it's a city. Yeah. So we can think of these classes, we can think of subclasses of classes. Yeah. So we can identify, for example, that capital city is a subclass of city, which means that if something is a capital city, it must be a city. Yeah. What other types of relations? If we look at the properties here, okay. Do we see any interesting relations? Anything we might want to capture? For example, let's say has capital city and has city. So if Chile has capital city Santiago, we could infer has city Santiago. Yeah. Anything else? We can maybe also infer has part. Yeah. So if Chile has capital city Santiago, and Chile has city Santiago, Chile has part Santiago, right? Potentially. What about between properties and classes? Yeah. So for example, is there something we can say about has capital city this property and capital city the class? So if we say Chile has capital city Santiago, what could we say about Santiago? It's a capital city, yeah. So we can define somehow that the values or the objects of has capital city, we would expect them to be capital city. What could we say about Chile in that case? We say Chile has capital city Santiago. We could maybe argue that it's a country. Maybe. Yeah, so we have 4 different types of relations that we just saw, and these are the core of the RDF schema that we're going to talk about today. So the first is the class hierarchy, which defines that if class C is a subclass of D, then if something's of type yeah, it's the sorry about the Zoom, it's the connection here is not great, but hopefully in the recording later it'll be okay. So class C is a subclass of class D. If X is of type C, then X is of type D. This is what it means. Yeah. So let's have a look at our example again. For example, if we have capital city is a subclass of city, and if we know that Dublin is a capital city, then we can infer that Dublin is a city. Which classes here would be subclasses of each other? Right, so we have one for free, which hopefully is the first one here, no spoilers. Capital city is a subclass of city, right? Any other possible options? Town and city. Town and city, okay. This one is a little bit argued. You could find that if you wanted, but sometimes towns are separate from cities. Yeah. What about city? Anything else here? Town and place. Town and place, yeah. And city and place. And country and place. And capital city and place, maybe. Okay, so we have town and place. We have city and place. We have country and place, and there's one left. It's actually implied by what we've seen. If we apply the transitive property of subclass. Yeah. So yeah, so we can add a dotted line here, which represents that we can actually infer this already. Yeah, it's already given because we have, if capital city is a subclass of city and city is a subclass of place, we can infer that capital city must be a subclass of place, right? So if Santiago is a capital city, it implies it's a city. If it's a city, it implies it's a place. So the subclass property is transitive. Yeah. Okay. So we'll look at property hierarchy next. So property hierarchy says if property P is a subproperty of C, and if XPY, then XQY. Yeah, so anytime we have the P relation, the Q relation must also hold if P is a subproperty of Q. For example, if has capital city is a subproperty of has city, and if Ireland has capital city Dublin, then Ireland has city Dublin. Yeah, makes sense? Okay, so which properties would be subproperties of each other? So we already caught the first one, which is has capital city is a subproperty of has city. Any other ideas? As city, does it have a subproperty? So we could say has city would be a subproperty of contains place, no? So if Chile has city Santiago, we could say Chile has place Santiago. Yeah, contains this place. Yeah. So we could maybe argue this. What about what about contains place? Does that have a subproperty? Family name, no. So that leaves the other option. Would it apply that if X contains place Y, then X has part Y? Seems pretty safe, seems reasonable to argue this, right? So if Chile contains place Santiago, then Chile has part Santiago, right? Somehow Santiago forms part of Chile. So we can argue this one. Any other subproperties? Any other subproperties for has capital city, for example? Yep. So we have the transitive property again. The transitive property applies just as it applied before. So we could say has capital city is a subproperty of contains place, has capital city is a subproperty of has part, and has city is a subproperty of has part, right? We do the transitive closure of the relation. Yeah. Any questions or doubts? Okay, so we have two more semantic properties that we want to consider. I hope the recording looks fine. It's recorded locally, so hopefully it should be okay. Just check everything. Yeah, that's fine. Okay. So the third semantic property that we're going to define is called the domain of properties. So we say if property P has domain class C, and if X P Y, then X is of type C. That's what it means. So essentially, for a property, we say if something has a value for property P, then it must be of class C. So, for example, if a full family name has domain person, and if Aiden family name Hogan, then Aiden type person. Yeah. So we say that family name is something that's defined on people. Now, one could argue that's not the case. That's fine. Then you wouldn't define that. Yeah. You wouldn't state this. So which properties would have which classes as domain? So has capital city, what would be the domain of has capital city? So remember, it's, for example, Chile has capital city Santiago. Country, could be, yeah. What about full family name? We could probably say person, yeah. What about has city? Maybe could be country, yeah. So full family name, we could say person, and contains place, we could say place. So well, that was a spoiler. We didn't get to that one. So if something contains a place, it must be a place, arguably. Maybe there's other things that can contain places that are not places. So has capital city, we could definitely say country, but it wouldn't apply then for example, states or regions. So we couldn't say that some province has a capital city of something. So it would be reasonable if we wanted to define that in our vocabulary, we could. Same for has city, that we could have a region, or we could have a province, or a county, or whatever it might be, a sub-region that has cities as well. So if we say that it's for country, then we can only use that property for countries later. So we have our fourth and final key semantic property, that is the range of properties. So we say property P has range class C. If this is the case, and if XPY, then Y is of type C. So somehow the dual of domain. Domain defines the type of the subject of the property. Range defines the type of the object of the property. Yeah. So for example, if has city has range city, then, and if Ireland has city Dublin, then we can infer that Dublin must be a city. Yeah. Seem reasonable? So which properties would have which classes as range here? So let's say has capital city would, if, yeah, could be city, could also be more specifically capital city. Yeah. What about has part? Doesn't seem to be a good candidate, no? Lots of things could have has part. If A has part B, it doesn't mean that B is a town, or B is a city, or B is a country, right? We can't really tell from that. Family name. So in this case, we don't have it, but the range would be maybe a string or a literal. Has city. Do we have a good range for has city? It would be city. Yeah. Contains place. Say the range is place, right? So has city, city, has capital city, contains place here, place, and I think that's about it. So there's some other options here actually. So has capital city, we could say the range is capital city, yeah? And if we know that capital city is a subclass of city, it gives us an inferred relation, yeah? So we could say, for example, or in this case, since has city has range city, and since city is a subclass of place, we can infer then that has city must have range place as well. It's inferred. Yeah. And likewise for has capital city, that we can infer the implied range here, and we can apply the another range for place. Yeah. So essentially it says that if some property has range C, and if C is a subclass of D, then property P has range D as well. So what does it mean? It means, for example, if has capital city, if we have Chile has capital city Santiago, then that means that Santiago is a capital city, it's a city, and it's a place. That's what this tells us. Yeah. So these are again inferred necessarily from what we're seeing. Okay. So there is a trade-off here. We have ways of defining the semantics of the terms, but what we define is up to us. Like, for example, when we talked about has city or has capital city, what would be the domain? Would it be a country? That's up to us. That's up to us to define. There is inherently always a trade-off in this sort of representation or in defining the semantics of terms, which is that we can be more specific, which gives us more rich inference, more rich information, but it makes what we're defining less reusable. Yeah. So what do I mean by that? If we took, so more specific means more conclusions, less specific means more reusable. So as an example, if we were to define that has capital city has the main country, that's fine. That's okay. We can argue that. The advantage is that now every time we use this property, we can know that anything that has a capital city is a country using this specific property. Yeah. However, we can no longer use this property for states or regions or provinces or whatever we might want to do. So there is inherently in any kind of language, there is this trade-off about being more specific but less reusable. Yeah, we can have more and more specific terms for more and more niche meaning, but it means that we can use those terms less and less. So the same applies in this case here. Okay. As another example, we might think that a mayor, alcalde, is a subclass of person. Yeah, seems reasonable, but not really. So there's lots of animals that have been elected mayors of towns. Yeah, so Bosco the dog was a mayor of a town in California, Sonal, lived from 84 to 90 or 81 to 94. Yeah, and there's been various animals, cats and dogs and all sorts of stuff that have been elected mayors. So anytime we go to think about defining something, often we can find exceptions to that. Yeah.
Is there a way to find that, for example, a mayor is a person, but make like an exception? Like a mayor is usually a person?
Yeah, so that's called something called defeasible reasoning. So it's sort of like the classic example is that birds fly, except for penguins. You know, this or emus, there's a few of them, right? But so in this sort of standard, it's not supported. Yep, there are other people who studied defeasible logic for that. So it's called defeasible reasoning, which is you define some general principle and then you define exceptions. And people have worked on some proposals for defeasible reasoning in the context of the semantic web, but it's more theoretical. So in what we're going to see, it's not possible, but there's some research on that. I think it's quite useful. Yeah, quite useful work. Other questions? Okay, another example, we could say a spouse has domain range person, right? So if something is married to something, then we could assume that they're people. But Erika Eiffel married the Eiffel Tower in 2007, right? So this would, if we were to use this property on this, it would mean that the Eiffel Tower is a person. Yeah. So this is also defined in Wikidata. If we go to the Wikidata, it will say that Erika has spouse Eiffel Tower. Yeah. If we had defined the range person, then we would infer that Eiffel Tower is a person. So we're sort of trapped in this trade-off of being more specific. That means essentially being more specific allows us to do more inference, but it restricts the reusability of the properties that we're using. Yeah. So another problem that emerged early in the semantic web was the problem of hidden definitions. Yeah. So this is more a usability problem. But as I mentioned, there's this famous or widely used friend of a friend vocabulary, FOF. This has been around since the start of the semantic web, and lots of people who are doing semantic web stuff started creating folk profiles to describe themselves in Turtle or in RDF XML and link to each other and create this social network. Within that vocabulary, it defines a property called FOF image, IMG. Yeah. And it states basically that an image can be used to represent something. Yeah. And then afterwards, it states that the domain is a person. Yeah. So can anyone see the problem? So it says image, and then it says an image can be used to represent something, and then it says domain is person. So if I say Aiden image something, some Aiden.jpg, that's fine. Yeah, Aiden is a person. But if I say Eiffel Tower, for example, image Eiffel Tower.jpg, what does it mean? Eiffel Tower is a person. So the problem here is that neither the name, and ideally the name should already indicate more or less what the thing is, nor the human description actually indicates to us that we should use this on people. Yes, it seems like we could use this property on anything we like. So there is this hidden kind of semantics here saying that if something has an image, it's a person, which is kind of not good. And this created a lot of problems because people saw image and they said, oh, I need to describe the image of something. I'm going to use image. And they don't see that. So any potential problems here? If we say, for example, Dublin image Dublin at night, then we're going to imply that Dublin is a person. Yeah. Okay. So it's kind of a gotcha in the semantics. So we don't want to have such gotchas or traps. So we need to choose the names of properties or classes carefully. So if we said, for example, instead of image, personal image or something like that, it would be much better. Yeah, we would avoid these sorts of problems. Yeah.
I don't understand this programming. It's defined as is. Can we use that specific property, or is this definitely something?
No, sorry. This one is a well-known property. We would say. So what's going to happen? Maybe to explain the general concept. Instead of every website and every data set creating their own vocabulary to describe people, which makes it a lot more difficult later to integrate the data, a lot of vocabularies have been defined on the web. And one of the oldest vocabularies or most well-known vocabularies on the semantic web is the friend of a friend vocabulary.
And why would these be defined? Why would image be constrained to being related to the person? Who said this gets this regulated?
So the maintainers, the people who define the vocabulary, and it's really a community kind of run thing. There are 2 or 3 people who proposed it and defined all the terms, and they receive feedback from the community as it gets more adoption. So I think they probably defined it like this because they thought from the start that this is for describing mainly people and the connections between people, who knows whom, what personal information. You can put some images, you can put your homepage, where you work. There is a vocabulary for that. So I guess based on the main use case, they decided that they would define the domain of this as person, because it's mainly for describing people, not thinking or not anticipating at that point in time that people might want to use this image relation for other stuff. So I think in general, it's not so easy to design very well. And this is one of the very earliest vocabularies. So this problem became relatively obvious later. They do have another property, which is FOF depiction, which you can use for anything. So FOF image is a sub-property of FOF depiction.
That sounds like a very bad idea. I would understand PFP standing for profile picture.
Yeah.
But this is.
Yeah, exactly. Yeah. So it's completely. I agree. Yeah. Not a good idea. So yeah, this is what I would call hidden semantics. The name of the property or the human readable description doesn't really tell you what's going to happen later when you start running reason. Yeah. Any other questions or doubts, comments? Okay, so this brings us to RDF schema more formally. So RDF schema or RDFS is a web standard, first released in 1999, I think, and then the first official recommendation 2004, and then a newer version in 2014. So it's been around for a while. So the editor is here, Dan Brickley, who actually was one of the key people involved with the full vocabulary we saw earlier, and Orbi Guha, who's very influential in the formation of RDF, both working at Google at this time. So RDF schema. So what is an RDF schema? What is in this recommendation, the specification that the W3C, the organization who organizes standards for the web, is recommending to everyone? RDF S or RDF schema allows us to describe some sort of schema, and I put schema in inverted commas because one could argue it's not really a schema, and people have done that. They're not in the sense of a relational schema that you saw in databases, for example. But it essentially allows us to describe subclass, subproperty, domain, and range relations. It gives us special terms for those in the RDFS namespace. Yeah. So essentially, if we want to say a subclass, we can use RDFS. So we can say a capital city is a subclass of city using RDFS subclass. We can say subproperty has capital city, RDFS subproperty of has city, domain, family name, domain person, and we can say range has capital city, range capital city, for family name, range, string, XSD string, for example. Yeah. So it gives us some well-defined standard relations that we can then define the semantics of and use to do some inferencing. So any guesses why RDFS calls this domain and range, these relations? Yeah, so it's very related to functions, right? So we have our function here, f maps x to y. So x in this case would be known as the domain of the function. Y here would be known as the codomain. And f of x, the actual values that are mapped by f from x to y, the actual values here that can be in a result of the function are called the image or the range of the function. Yeah. So essentially x is the domain of the function and y is the codomain of the function. And this here is the range. Yeah. So what's the point? We can somehow see properties as mapping from subjects to objects. Yeah, and then we say what type of subject it is and what type of object it is. Now, properties are not functions because we can have multiple values for a single value of x. For a single subject, we can have multiple values. So it's not really a function, but the intuition was used for the naming of the relations. Okay, so we can think about modeling an RDF schema for movies, including different types of movies. We have horror movies, comedy, action, some different types of people involved, and how they are related. Yeah. So let's just talk about it for a bit and see. So we have movies, and we have different types of movies, such as horror, comedy, and action. How would we model the different types of movies using RDFS? One possible way. So one option would be to create a genre property and relate movies using the genre property to horror or comedy or action. Another option would be to use classes, right? So we could define a horror movie, a comedy movie, an action movie. And how would we relate that to movie? Subclass. Yeah. So we could say if something is a horror movie, it's a movie, right? Some different types of people involved. So we have actor, producer, and director. So again, one way to model this would be to create a property which is occupation or profession, like what the person does for a living. Or the other option would be to create classes for these different types of people. Yeah, so actor, producer, director. Yeah, and we could then define subclasses. Yeah. And then we can create different properties and relate these. So here's an example of an RDF schema that we might come up with. Here we have decided to use this MOF, which is an example, although there are movie ontologies that allow you to do something similar. We have different types of people involved in movies. We have producers, directors, actors that are all subclass of person. Yeah. We have different properties, for example, produced, directed, acted in to relate the movies to the people. And we can define the domains of these to be actor, director, and producer. And we have this other relation starred in, which allows us to define to specialize the property of acted in. So if somebody not only appeared for maybe 5 seconds in the background, but also was a main actor in the movie, we can use the special relation starred in, and we define that to be a subproperty of acted in. Yeah, so then we can say starred in has the main actor, acted in has the main actor, and so forth. And finally down here, we can say that all these things point to movie. Okay, this is again quite specific because people could also direct or act in TV series or TV shows, whatever it might be. In this case, we're defining it this way. which means that if we use this directed property, it means that the object or value of that directed property is a movie. And then we have these different subclasses of movies like horror movie, comedy movie, and action movie. Yeah. So this is one possible way in which we could define this sort of setting using RDF schema. Okay, so there's some arguments here. We could argue about the modeling. We could say that probably actually the range of directed shouldn't be movie. It should be more general. It should be creative work, maybe something like that. People might argue as well that really actors are not subclass of person. It's two different things. There's a person and there's an occupation or what they do. You know, it's not really a type of person. A director is not a type of person. Yeah, so that's also fine if you want to argue that. One could also argue that a comedy movie is a compound statement. So I mentioned that briefly in lab 2. It's sort of you're mixing two things, and there's no real need to do that because the permutations or the combinations become very large. So rather than say something as a comedy movie, in general, it's better to say it's a movie in one statement and that it's a comedy in the other statement. So we can then find all the things that are comedies that are movies or books or TV series or whatever, right? But this allows us, at least using RDFS, the sort of more limited vocabulary, and we'll see much more expressive things later without. This allows us to do some inference within the movie domain. So there are some arguable, maybe things we could argue or debate about here, but as an example, it's useful to start with. So what is the domain of has part? So domain again means that if something has part, then it's in a particular class. So if we say that X has part Y, what would the class of X be? Could be anything, right? I have parts, this building has parts, this country has parts, this microphone definitely has parts. And so it could be anything, yeah? So in RDFS, we have some meta terms, some meta vocabulary that are useful to describe more formally the semantics of the vocabulary itself, of RDFS itself. So the first meta vocabulary we have is RDFS resource. And what is RDFS resource? It is the class of everything. Everything is an RDFS resource. Everything is an RDFS resource, yeah? If you want to ask, is something an RDFS resource? The answer is yes. Is RDFS resource an RDFS resource? Yes. A resource is a resource. Everything's a resource. Yeah, everything in RDF is a resource. So RDFS resource is in RDFS resource. Yeah. So it's also a resource. So if we say that the domain is resource or the range is resource, what it means essentially is nothing. It tells us nothing, because it tells us that the subject or the object of the property is something. Could be anything. Yeah. However, it's often found in vocabularies just to let people know, you know, this is the intention. It could be used for anything. You can use this for anything. Yeah. So it's somehow, it's not that the thing is omitted, but really the intention here is that you can use this property on whatever you want. So we also have some other meta classes. We have RDF property, which is actually in the RDF namespace. Just to mention, some of the things here are defined in RDF and some of them are defined in RDFS. If you mix up the RDF or RDFS namespace, the stuff won't work. So because these are special reserved vocabulary, you need to get the namespaces right for this. And this will happen in the lab as well. It's a common problem. So how do you remember it? Basically, you kind of just have to memorize some of these terms and where they are. So it's RDF type, but RDFS subclass of. It's RDF property, but RDFS resource. Yeah. So RDF property is the class of all properties. So we can say, for example, that has city is of type property. And we have RDFS class, which is the class of all classes. So we can say, for example, that city is of type RDFS class. And again, we see it's RDF property, but RDFS class. So this is kind of a little bit messy. They could have, you know, done a cleaner job of this, but it wasn't clear what was needed when they started standardizing these things. Okay, so a common point or a common point of confusion, a common source of errors or problems when modeling in RDFS is the notion of something being a class or an instance. So earlier I told you that resource is a resource. Yeah, so it's sort of resource is both a class and resource is an instance. So the question here is, how would you define oak, this species of tree? Would you define it as a class or an instance? Yeah. So how, if we choose between class or instance, would we say that oak, the concept of the tree species, is it a class or an instance? Yeah, okay. So what would it be an instance of oak? You could argue, but I would be a little bit more specific. Yeah. What would it be a subclass of? Tree. So what would it be an instance of?
Plant?
No, it would be a subclass of tree, and if tree is a subclass of plant, it would be a subclass of plant. And oak is a type of what? Tree species. Yeah. I mean, we can define this however we want, but there's, you know. So, okay, here we have an example, right? So we have the Bowthorpe oak, which, if I remember, is some very, very old oak somewhere, the oldest tree somewhere in Europe or something. I don't know. We have this famous oak, the Bowthorpe oak, which is of type oak. Yeah, so what can we say about this specific tree? The specific tree, we could say that it's an oak, and if it's an oak, it's a tree. Yeah, so the Bowthorpe oak, it would make sense to say that it's of type tree. Yeah. So what does it mean? That it means that anything that is of type oak should be of type tree. And that means that we put the subclass relation between oak and tree. Yeah. On the other hand, Bowthorpe oak, here we have stated that oak is of type tree species. Yeah, it's an instance of tree species. Would we say that Bowthorpe oak is of type tree species? No, it's not a tree species, right? So we see that here we're not going to get this inference, right? Because it's type, and type is not it's not transitive, right? So in this case, the inference we'll get is that Bowthorpe oak is of type tree, but we're not going to infer that Bowthorpe oak is of type tree species. Okay, so classes can also act as instances. There's no strong distinction here in RDFS. It can be, something can be a class, it can be an instance. There's no problem with that. In general, if we want to think about it, or we want to maybe try to conceptualize it or map it to something we already know, RDF type is akin to in, as in set membership. Yeah, this something is in the set. Yeah. Whereas subclass of is sort of akin to subset or equals. Yeah, of the sets. Yeah. So in this case, what we're saying is that oak is in the set or class of tree species. Yeah. Oak is a subset of trees. Yeah, so all of the things in the set of oak are in the set of trees. Bowthorpe oak is in the set of oak. Yeah, so this is sort of set membership here. Yeah, so there is a little note here that there is a difference between classes and sets, but for the moment, it's a fine intuition, and they're highly related. But we'll cover this a little bit later, more formally, what the difference is and why we need to be a little bit careful about this. So that's why I say akin, kind of similar or related to. Yeah. So it's a useful intuition to have. So based on this, which would you say is transitive based on this intuition of RDF type being like set membership and subclass of being like subset? Which would you say is transitive, RDF type or subclass of? Subclass of, right? Yeah. So subclass of and not type. So for example, here we have Bowthorpe oak type tree species. We do not want to infer that Bowthorpe oak is of type tree species. We don't want it to be transitive. If we had white oak, and white oak is a subclass of oak, and oak is a subclass of tree, then it's perfectly fine to infer that white oak is a subclass of tree. Yeah. So the transitive property is perfectly okay in that case. Okay. Any questions or doubts about that? So as we see in the real world, there's no real strong distinction between something that's a class and an instance. Yeah, maybe in programming languages or in other settings, sometimes we make these strong distinctions. That doesn't really happen in the real world. Something that's a class can also be an instance of some higher level categorization, right? As in this case, an oak is a tree species, but it's also a subset or subclass of trees. Questions or doubts? All good. Okay, so we're going to turn to the topic of reasoning, and it might be useful just before we get into details. to talk a little bit about reasoning, because we've seen reasoning before, maybe in other courses, maybe not actually. So we need to talk a little bit about what we mean when we talk about reasoning. So reasoning in general is this concept of being able to automatically, at least in a computer science sense, no, in a human sense, we can also do reasoning, to draw conclusions or deductions from observations. Yeah. So does anyone know what kinds of logical reasoning we can consider? Has anyone heard of different types of logical reasoning? Does anyone know, for example, sometimes people talk about inference or reasoning in the context of machine learning. Does anyone know what type of reasoning we're applying in machine learning in most cases? What kind of reasoning we apply? Or what kind of reasoning we apply when we apply things like logic, first order logic? Yeah, so logic would be deductive reasoning. And if logic is deductive, what is machine learning? Inductive. Yeah. And there's a third type that's not so well known that we'll cover soon. Yeah. So what is reasoning? So if I tell you all movie directors are human and Anthony Ferrante is a movie director, what could you imply from that? Anthony's human, right? Anthony Ferrante must be human. We can be sure of this. Yeah. Relatively sure. So deductive reasoning. This is deductive reasoning. It's basically making logical conclusions from rules and premises. Yeah. So all movie directors are human. Anthony Ferrante is a movie director, therefore Anthony Ferrante must be human. This is just one type of deductive reasoning we can apply, but this is the illustrative example of the type of thing we can do. Sharknado. So the first 3 Sharknado movies were great. What could we maybe say about the 4th one? That's not out yet. Yeah, we could probably figure that, okay, if the first 3 were great, then the 4th one's bound to be great, right? So we can say Sharknado 4 will probably be great too. We can't say it with certainty, yeah, but based on what we've observed, we can maybe predict something for the unseen data. Yeah. What would this be? Inductive reasoning. Yeah, it's a very simple example of an inductive reasoning. So what we're doing here really is learning rules. We're learning some model or some way of predicting, what's coming. So in this case, the approximate rule that we're applying is that Sharknado implies great. Yeah. So that's inductive reasoning. The third type that's not really so spoken about, these are kind of the main 2, deductive, inductive. But there is a sort of a distinction with a third type of reasoning, which is somehow a mix between both. It's neither, strictly speaking. Which is as follows. So Fred saw a movie with sharks in tornadoes. Sharknado movies have sharks in tornadoes. What could we possibly suggest here?
It's amazing.
That's also true. Yeah, we could probably try to explain what happened, right? So we could say that Fred may have seen a Sharknado movie. We're not sure, but based on this, it seems quite likely. The classic example is we have a rule, which is if it rains, the streets will be wet. Yeah. And if we see that the streets are wet, we could guess that it probably rained. I mean, there are other possibilities. Maybe somebody went with a hose and wet all of the streets in the city, but it's more likely that we can explain the streets being wet by there having been rain. This type of reasoning is called abductive reasoning. It's somehow, the idea is to guess or propose a premise that that gives us that explains something. Yeah. So kind of what led to this point? What was the premise that based on the rule and the conclusion, what might the premise have been? So as a summary, if we try to organize these a little bit better, so we have 3 different things here. The first thing is a rule, which says that if F is of type Sharknado, then X depicts Sharknadoes and tornadoes, or Sharknadoes and tornadoes, sharks and tornadoes. So this is maybe not the best modeling, but hopefully it's understood. So if X is a Sharknado movie, then it has sharks in tornadoes. It's about time. I think it's the third one, is of type Sharknado movie. It's about time depicts sharks in tornadoes. Yeah. So we have essentially a rule, a premise, and a conclusion. Yeah. So we have these three different elements. The three different types of reasoning then omit something, and we have to figure it out. Yeah. So in the deductive reasoning case, given 1 and 2, we want to conclude 3. So given the rule and the premise, we're certain about the conclusion. Yeah. So if X is type Sharknado, then X depicts Sharknadoes, sharks in tornadoes. It's About Time is a Sharknado movie, therefore It's About Time must depict sharks in tornadoes. Yeah. So inductive reasoning. In inductive reasoning, what are we given and what have we to propose or give? So in inductive reasoning, typically we're not going to have the rule, the pattern, the model, yeah, the general quantified thing. Yeah. So all we have is just data. It's like facts or information or data. And we have to extract a higher level or propose a higher level pattern or model or rule for that. Yeah. So in this scenario, the inductive case would be given 2 and 3 and lots more data like this, propose 1. Yeah. So this would be the sort of inductive reasoning case. So in the inductive reasoning case, given 2 and 3 and lots of similar such examples, if we see that, oh, in our data, every time something is a Sharknado movie, it depicts sharks in tornadoes, then we can say, okay, well, we can propose this more general rule and apply it to unseen data. Yeah. And abductive reasoning, you could probably guess. Anyone want to guess? So it's given the rule and the conclusion, which would be 1 and 3. We're going to propose 2. Yeah. So this is abductive reasoning. So given 1 and 3. So Sharknado movies depict sharks in tornadoes. It's About Time depicts sharks in tornadoes. Therefore, we could probably guess the reason that is because It's About Time is a Sharknado movie. Yep. Okay, so we have these 3 high-level types of reasoning. Deductive, inductive, abductive. The 2 main ones being deductive and inductive. Abductive is often seen as a way of generating explanations. Questions or doubts? Okay. So we're mainly in this course going to be talking about deductive reasoning. We're not talking about the sort of inductive machine learning, large language model, deep learning type of reasoning. We're going to be applying more logic and rules and ontologies to get certain conclusions from definitions. Assuming the rules and the premises are correct, the conclusion will also be correct. And that's a big assumption that the rules and premises are correct. But okay. So RDFS reasoning is deductive. We're going to apply some logical conclusions to our definitions, to our axioms, to our data. It's the only form of reasoning that we've seen, at least of these 3 here, that is certain. Yeah. So if the rules and premises are fine, then the conclusion should be fine as well. So we saw this RDFS schema that we defined earlier with action movie, subclass of movie, and actor, subclass of person, and directed domain director, and so forth. So this is all well and good, but what do we use this for? The idea is we can use this for deductive reasoning. So if we're given a fact, for example, afterwards that Eric Roberts starred in Sharktopus, sorry, I was about to say Sharknado, Sharktopus, what could we infer based on our RDF schema? So if Eric Roberts starred in Sharktopus, what could we start to infer? So we're given this schema, these definitions here of subclasses, subproperties, domains, ranges. We're given this triple here. So the first thing, maybe it's a little bit difficult to read, so we'll go through it. This says starred in, subproperty of acted in. Could we apply this axiom to this triple here? Yeah. So we could say, for example, Eric Roberts acted in Sharktopus. If she starred in Sharktopus, or he starred in Sharktopus, then he must have acted in Sharktopus. Yeah. We have starred in is range movie. So what could we conclude here based on starred in range movie? The Sharktopus is a movie. Yeah. Now this might be incorrect if this were a TV series or something, but okay, according to these definitions, if we hold them to be true, then Sharktopus must be a movie. We have starred in is a where is it? Starred in here has domain actor. What can we say about Eric Roberts? He's an actor. We have actor as a subclass of person. What can we say about Eric Roberts? Yeah, so now we're getting recursive, right? So we are now applying inferences on inferences. Yeah, so Eric Roberts is an actor based on the domain. An actor is a sub class of person. So now that means that Eric Roberts must be a person as well. What else can we infer? Lots of things. We can infer lots and lots and lots of things. We can infer, for example, that Eric Roberts is a resource, because everything is a resource. Yeah. We can infer that starred in is a property because we use it as a property. Yeah. We can infer that actor is a class. We can infer that actor is a subclass of actor. Everything is a subclass of itself. We can infer that starred in is a subproperty of starred in because every property is a subproperty of itself. Yeah. So we get a lot of boring inferences there. Yeah. So here is some of the stuff we get. So we get all the interesting stuff we found. Eric Roberts starred in, acted in Sharktopus. Eric Roberts is a person. Sorry, this should be fourth person. Eric Roberts is an actor. An actor is a subclass of itself. This could be a subclass of itself. Movie is a subclass of itself. Property is a subclass of itself. Everything is a subclass of itself. All the properties are subproperties of themselves and so forth. So this is not even complete, right? There's a bunch of other sort of more syntactic stuff that we can infer from this, like that everything is of type resource, that all classes are subclasses of resource. If something is a person, it's a resource. So therefore it means person is a subclass of resource. And there's a bunch of other syntactic stuff. All RDF or RDFS properties are of type RDF property. Okay, but the cool stuff here is that we can at least figure out, or based on this simple triple and this definition, we can figure out that Eric Roberts is an actor or person. This is a movie. This implies the acted in relation and so forth, right? So we can start to do some automated inference, deductive inference on this. So Sharktopus is just one movie, one very important seminal movie, but we can also have other movies, right? So we can take this exact same example, and the idea isn't just to define all the schema for Eric Roberts and Sharktopus. We can change this and we can say, okay, now we're looking at another movie. Let's describe somewhere else on the web. We have Eva Hasberger starred in Dino Shark this time. So what can we infer? Exactly the same sort of patterns. Yeah, we can apply this to any movies, any actors we find, right? Any data using the schema that we can find. So the idea is, if we do a good job of our vocabulary, we can think about it, we can model it, define all of the semantics, publish it on the web. And if other people reuse that on the web, then all of the data sets that use that vocabulary, we can apply this sort of deduction to. Yeah. So this is the core idea that we're getting. So we can define this schema once, do a good job of it, publish it on the web, and then tell people, hey, I have this new schema or ontology describing movies. If you want to describe movies on the web, you can use this and you can get all these cool inferences out of it. That's the core idea. So yeah, what can we get out of this? As we saw before, it's the same stuff. We just replace Sharktopus with Dino Shark and Eric with Eva, and we get the same sorts of inferences again. So how do we get these inferences in terms of algorithms? How do we actually implement this? How do we, write some code that will get these sorts of inferences from what we saw? So the core idea is to apply reasoning using rules. Yeah. So these are rules that are not defining, for example, that a movie that an actor, if something is an actor, then it's a person. These are higher level rules that are standard. They're applied always equally over whatever schema. Yeah. So what are some examples? They effectively axiomatize or tell us how to reason about the RDF and RDFS vocabulary itself. So let's look at some examples. So for example, RDFS2 is a rule that says if P and these question marks represent variables that can somehow match to whatever is in the data. So we say that if P has domain C as X, P, Y, what can we infer? It says that X as C, and the A here is for RDF type. Yeah. So P domain C, X, P, Y, X as C. So for example, if we say P family name domain person, Aiden has family name Hogan, then Aiden is a person. Yeah. So we have one here, which is RDFS3, which we need to figure out. We have P range C, X, P, Y. That's the body of the rule. That's the thing we need to match. P range C, X, P, Y, what could we infer from that case? We can infer that Y is of type C. Yeah, Y is of type C. Okay, so sorry, some things are grayed out because they're more syntactic. They're for certain features that are considered more syntactic, but okay. So we have Y as C. So in this case, we have P subproperty of Q, X, P, Y. What can we infer from this? P subproperty of Q, X, P, Y. So an instance of this would be has capital city, subproperty of has city. Chile has capital city, Santiago. XQY. See? So Chile has city, Santiago. So we get XQY. We have some other examples here that you can go through a little bit later. We'll take one last one here. RDFS 11. We have C subclass of D, D subclass of E. C subclass of D. I'm not sure if that's, yeah. So we have the transitive property, right? So if we have, for example, a capital city is a subclass of city, city is a subclass of urban area, then we can say that capital city is a subclass of urban area. Yeah, this is the transitive property. So C subclass of E. So these are basically all of the rules that we need to apply. We can apply these recursively until we just don't get anything new. Yeah. So this is the RDFS reasoning work. So there's also some list of what are called axiomatic triples that we can add to our inferences that are always true in RDFS. These are kind of more syntactic elements. So for example, we have that type is a domain resource range class. So we define the domains and ranges and subproperties and subclasses of the RDF and RDFS terms themselves, which is kind of a little bit strange, but these things always hold true. So we could say domain has domain property, has range class and so forth, and we get all of this stuff here. And at least left some stuff in gray that are more syntactic elements that are not so important for us. Yeah, but they're part of the full list of axiomatic triples. So for applying reasoning, there's two steps. We can add axiomatic triples to our RDF graph. So we add in these triples that are always true. We run the rules until we find nothing new. And we're done. We've created this larger graph that contains all of the inferences or things we could conclude deductively from the definitions. So there's a question here. Will this always finish or can it run forever? So will this reasoning process finish? Do we have a way to figure out will it, because we know there's recursive stuff, right? So we know that if something, if we infer one thing, it can trigger the inference of a new thing. Okay. And the question is, will it finish or will it always finish or can it run forever? And this is a big deal when we talk about reasoning. It's like, is it decidable? Can we actually build algorithms that will finish with some sort of answer for this problem? In this case, we can say that it finishes. There's a kind of an asterisk to that because we have a graph. Yeah, we have a graph. We have a finite amount of vocabulary and we have a set of triples. So essentially, we can say that if we take all of the terms and we put every combination of terms possible in the graph, then we can no longer possibly conclude anything more. It's just impossible. Yeah. Once we have reached the point where we have the vocabulary times the vocabulary times the vocabulary, we can't do anything more. Yeah. So essentially, so long as we do not invent new terms and axiomatic triples are finite, these are the asterisks I'll have to come back to, the process must terminate once G has all possible combinations of terms as triples. Yeah, because G is a set, and at some stage, we're just going to have all possible triples that we can create from the finite vocabulary, and then we can't possibly ever infer anything new. Yeah. So it must finish. So there's some asterisks here because actually the set of axiomatic triples is infinite because there's some syntactic thing here that we never spoke about that allows you to define the first element of something, the second element of something. And it has within the vocabulary an infinite number of terms. So you can have RDF underscore 1, RDF underscore 2, RDF underscore whatever number you want. That actually means that this is infinite, but this is just kind of noise. Is in the standard. That's not particularly useful. So in general, we can take these RDFS axioms, they're described in RDF, and we can apply rules to get some conclusions. So, and it will finish. So at some stage, we're not going to find anything new. We know this for sure, and then we're done. Yeah. Any questions or doubts about that? Okay, so that's the first approximation of the logic layer for the semantic web. RDFS is a relatively unexpressive but very useful standard. It's sort of like the basic stuff that we might need to define the semantics of terms. There's still a lot of stuff that we'd like to define. In fact, neither of these rules here we can define using RDFS. We can't do something similar using RDFS because B capital A implies A part of B. There's no way to express that because we need to flip the direction of the edge. Yeah, this is inverses, which we'll see the next time. A part of B, B part of C, this is transitivity. Although subclass is transitive, we don't have a way to define that custom properties are transitive. Yeah, so we can't either represent this sort of rule, unfortunately. So we'll have to see this the next time when we look at a more expressive language called OWL for this. So RDFS is a web standard. It's been around a long time. It's been used quite a bit. It's also, there's been, for example, definitions of this for schema.org for some of the vocabularies that are widely used. And we're going to see it in the lab on Wednesday. So we're going to be defining some RDF schema, and then we're going to see how what deductive conclusions we can take from that, what inferences come out, and how it enriches the graph. So yeah, this is the first class on this sort of topic. There'll be 3 more classes that are going to get progressively more deeper into this topic of knowledge representation and its limits. Any questions, doubts? No, all good. Okay, so see you on Wednesday.